Never felt that, come on, yeah. Never felt that, come on, yeah. When I never felt that, come on, yeah. You gotta get up.
This one is a little long, so we've broken it down into two parts. Here's part one.
Layers of the earth. Layers of the earth. Throw your hands up for layers of the earth. Throw them up for what's below the surface. Throw your hands up and let's discuss the inner core, outer core, mantle and crust. Throw your hands up for the layers of the earth. Throw them up for what's below the surface. Throw your hands up and let's discuss the inner core, outer core, mantle and crust. The layer we'll discuss first is the central inner core in the center of the earth. A solid ball buried below the dirt.
We believe it's primarily metallic iron.
You can never take a trip to the inner core, right? The heat will burn you up 9,000 Fahrenheit, 4,000 miles below the Earth's crust. One down, three to go, y'all. 1,800 miles from the tip top. The outer core is hard at work and it don't stop. It's busy spinning around the inner core.
And listen,
This steady movement causes Earth's magnetism. Ranging from 4 to 9,000 degrees, it contributes 1/5 of the heat flowing to you and me. It's liquid metal that violently flows. So let it settle when you're ready, let me know. Just throw your hands up for the layers of the earth. Throw them up for what's below the surface. Throw your hands up and let's discuss the inner core, outer core, mantle and crust. Throw your hands up for the layers of the earth. Throw them up for what's below the surface. Throw your hands up and let's discuss the inner core, outer core, mantle and crust. The mantle layer is the largest of the class, about half of our planet's mass. The mantle is composed of very hot, dense rocks that move and flow, always on the go. They never lie, never stop, and responsible for tectonic shift.
please believe.
Earth's plates are adrift. It's pretty thick, y'all, and the heat is awesome. 1,600 at the top, 4,000 at the bottom. The continental crust surface is where we breathe. A lot of rock up to 25 miles deep. The oceanic crust is just next door. It's 3 to 5 miles thick below the ocean floor.
Earth's surface?
70% H2O.
Where you get all that water?
Salty sea flow. The rest is fresh water in the glaciers, ice caps, and snow.
Let me see you throw 'em.
Throw your hands up for the layers of the earth. Throw them up for what's below the surface. Throw your hands up and let's discuss the inner core, outer core, mantle and crust. Throw your hands up for the layers of the earth. Throw them up for what's below the surface. Throw your hands up and let's discuss the inner core, outer core, mantle and crust.
Flying past the Earth at this time, we see a vast gray ocean beneath a red-tinted sky, punctuated by volcanoes and small land masses. And unlikely as it seems, life may have gained a foothold already. That life in the oceans that gave birth to it may actually be vaporized many times by cataclysmic bombardments, which have slowed but not yet stopped. Earth has begun to take on its final form, a crust, a skin so thin it would be less than a sheet of paper were the Earth the size of a basketball. And under that, a molten semi-solid mantle that boils in extreme slow motion. And finally, two cores, a liquid iron core pulsing out a magnetic field that helps shield us from a deadly cosmic wind from our sun. And a solid nickel and iron inner core. By now, the remarkable process of plate tectonics has kicked into gear. Though how and when it started exactly, we do not know. For what follows next, you might want to strap yourself in. It's going to be a bumpy ride. Here's how it might have happened. At first, Cretans and one continent called Ur had the planet all to themselves. Then, around a half billion years later, Antarctica took shape. About another half a billion years passed before Atlantica formed. The continents roamed separately until, about 1.8 billion years ago, Antarctica collided with what is now Eastern Antarctica to form Nina. Then Nina, Atlantica, and collided 1 billion years ago, forming the supercontinent Rodinia. After about 300 million years, the three landmasses separated and came back together in a new configuration, Pangaea. Pangaea came apart too. When Pangaea split, and Atlantica split up too. If you're confused, join the club. Even the Earth seems confused. All of this movement made for a host of unlikely neighbors way back when. North America's eastern seaboard once rubbed shoulders with Chile. California and Australia were neighbors, if not connected. And Brazil was either connected to Nigeria or very close. Run the Earth time machine backwards, and you can see why. But no matter how many times you run the demolition derby of the continents, a question remains. What the hell is driving them? Hell, apparently. The force driving the plates is the slow movement of the super-hot semi-solid mantle that lies below the rigid plates. Like hot soup, magma boils in slow motion. Superheated magma rises to the surface, begins to cool, and then sinks back down to the bottom of the pot, where it is reheated and rises again. This cycle is repeated over and over to generate what scientists call a convection cell, or convective flow. But where's the heat source keeping our earthy soup performing its circular gymnastics? Well, most of it is left over from the spectacularly energetic collisions and gravitational crushing that created the Earth to begin with. It's still trapped down there, and it wants out. And there's something else in the molten depths that makes it pretty hot real estate. Radioactive material. The belly of the beast has plenty of uranium and other radioactive elements, all of which release heat as they decay. That decay has significantly slowed the rate at which the Earth is cooling. So what does this mean at the surface? Two things. First, magma being burped up along the ridges, those places like Iceland where the Earth is tearing itself asunder, is pushing the plates in their respective continents apart. Second, what goes on at the other end of those plates, the collision zone, may be equally important. Here, where the heavier plates dive under the lighter ones, yanked downwards by gravity, they haul along their plates back into the oblivion of the mantle. That's what we know, or what we think we know. But the details of what's going on in the deepest parts of the Earth that drive the engine of plate tectonics, we may never know.
Let's take a closer look at that. No, not that Ring of Fire. This Ring of Fire. Imagine how good this would be if Mr. Richards was singing it.
Hi. Hi. I'm not Johnny Cash, but I have been in a Ring of Fire. Seduction is a burning thing. It needs a fiery ring. cold dense ocean floor will soon retire. Down through the mantle for a ring of fire. Subduction scrapes off mud round a burning ring of fire. Takes water down, drives the volcanoes higher. Makes light and aside from a ring of fire. A ring of fire. The soul is born calm and dark. Spreading ridge or Hawaii's hotspot hard. Dangerous stratovolcanoes, fountain higher. Wind fed by subduction and a ring of fire. Subduction scrapes off mud round a burning ring of fire. Takes water down, drives the volcanoes higher. Makes light and decide. And a ring of fire, a ring of fire. Great earthquakes from the moving load. Stick, slip, and place, its mighty implode. Eruptions, landslides, we require. Tsunami warnings from the ring of fire. Subduction scrapes off mud round a burning ring of fire. Takes water down, drives the volcanoes higher. Makes light in the side from the ring of fire. The ring of fire. St. Helens blew high, others blow higher. Going on fear.
And that's part one. Thank you for watching.